We left off talking about the enthalpy change and whether or not reactions are endo or exothermic, and so now we're going to talk about how we find the heat of formation and how we find that H value that will help us find the total enthalpy change of a problem. So the heat of formation is just the energy either absorbed or released when an element or a compound forms from its elements, and so if the change in H is very negative, then the compound is very stable. If the change in H is a positive value, then that means that the compound will decompose. And so our elements then, because it's the energy absorbed or released when a compound forms from its elements, the elements then have a change in H of 0 because they're not going to form from anything. So when we look at your blue sheet here, so that you should have this, and this is your blue sheet. So our elements, just showing you by themselves right here. So any element by themselves should have a change in H of 0. So there's our value. This column is what we're going to be looking at. And then we can look at here, that's a relatively large negative number, so we can assume that that's pretty stable. And then here, again, a lot of negative numbers. Here this is a positive number, so we can assume that that's not very stable. And then on some of them, please watch the states of matter. So for example here, this is water in the gas form, and this is water in the liquid form, and they do have different values. So watch your states of matter when we're dealing with compounds and finding the heats of formation. These values down here are the heats of formation, and these will be helpful especially when we do some of our labs. Our fuels lab, we will use these, and our Hess's Law acid and base lab, we will use these. So just kind of an extended on compound list for us on the blue sheet that wasn't necessarily included in the table. So the heat of combustion is the heat released by the complete combustion, or which means burning with oxygen, when 1 mole of fuel combusts. So fuels combust, remember our combustion equation is a fuel plus oxygen yields carbon dioxide and water. And then we know that this is a thermochemical equation because it's telling us it's releasing 2,219.2 kilojoules per mole. So again, this is the heat of combustion of C3H8. Please note that it's not the heat of formation value. So those are two different values. So if you look on the back side of your blue sheet, it shows you the heat of combustion values. So we're going to actually use the heat of formation values to calculate the heat of combustion. So this page is going to help us with accepted values after we have calculated the experimental change in H of combustion using the change in H of fusion values from the front. This will come in really handy when we do our fuels lab. So when we do our Hess's Law acid and base lab, it's not going to be that much, but when we do that much of a difference here where we're going to have to really focus on what side of the page we're dealing with. But when we do the fuels lab, we're going to have to make sure that we use this only as the accepted values to help us calculate our percent error, and this to help us actually calculate what our lab heat of combustion will be. And then this just is reminding us to calculate the change in H of combustion. We use Hess's Law, which is the products minus the reactants, and use the heat of fusion to calculate the heat of combustion. So there's the equation for Hess's Law. So again, Hess's Law is the products minus the reactants, and you talked about that when we were dealing with the change in H of either an endothermic or exothermic reaction. So if we have methane here, we know that it's CH4 plus oxygen yields water and carbon dioxide. And so when we want to find our change in H values, we're going to go to our blue sheet. So I've circled them here for you. So our change in H value of CH4 is negative 74.9. Of carbon dioxide gas is negative 393.5. Liquid water, so again watch your state of matter, is negative 285.8. And then oxygen is 0 because it's an element. So all of our element heat of formations are 0. And so here what I understand that for it to make 2 waters, I know that it's 2 times negative 285.5 because there's 2 of them in the balanced equation here. I know that to make carbon dioxide it releases negative 393.5, and then to make CH4 is negative 74.9. So I'm just identifying and finding my values from the blue sheet. And then what I want to do is I like to add them into underneath the chemical formula so that I don't make any mistakes when I'm doing my products minus my reactants. You don't necessarily need to do this step. It's just become a habit so that I make sure that I don't make any mistakes when I'm plugging in my math formula. So In order to show my work, what I'm going to do is write out what my products minus my reactants are going to be. So I have 2 waters plus a carbon dioxide, and I'm going to subtract that from the reactants, which is methane and oxygen. So I'm going to write that in to show my work. And then what I'm going to do is what your problem and what your paper should look like is this already written, and then you can write the values right underneath. So you can plug in the negative 285.5 right in the space for water, and then negative 393.5, and then negative 74.5, and then 2 times 0, and I know it's redundant because you know it's a 0, but please just do that to show your work. Biggest pitfall here is watching your positives and negatives when you put things into your calculator. And so my value ends up being negative 889.6 kilojoules per mole. So go ahead and pause the video and make sure that when you do your calculation in your calculator that you're getting the same value. So hopefully you pause the video and we're able to confirm that it's negative 889.6, really just again watching your positives and negatives. So again, your work should look like this. You don't need to rewrite it every time. This is just how the slide is showing up for me when I'm doing the notes. And so this is our experimental heat of combustion, and we found that experimental heat of combustion by using the heats of formation. So hopefully those vocabulary terms are becoming comfortable. So our heats of formation, again, are the energy released or absorbed when an element forms from its compounds. The heat of combustion is the energy released when 1 mole of fuel burns. So we use the heats of formation to calculate the heat of combustion. So we can check on our blue sheet on the back, there's CH4, and we look that our calculated heat of combustion is very close to the accepted value. Alright, so now we're going to flip to the Hess's Law sheet and take a few more notes, and I'm going to teach you how to calculate Hess's Law both the long way and the short way.